Manager on the Azure Databricks team. And with me, I'm fortunate to have Sean from Databricks. Sean, you want to introduce yourself?
Yeah, I'm Sean Owen from Databricks. I'm a data science lead there, and I may know some of you from working on the Apache Spark project, where I'm a committer and PMC member. And today, hopefully, I'll show you a little bit of Spark, a little bit of Databricks, and a little bit of deep learning as well.
All right, thanks, Sean. All right, so the agenda we have planned for you is we want to first talk about deep learning to sort of level set on what deep learning is all about, just to make sure. By the way, just a show of hands, how many folks here know deep learning or have worked with deep learning or have at least heard about it? A few folks.
Explain it in a couple sentences.
Yeah.
Okay, all right.
Thank you. What about Azure Databricks? Is folks in the room have heard about? Oh wow, that's quite a few. Good to know that. How many have worked on deep learning with Azure Databricks? So I'm glad that, I'm hoping you'll get something out of this session. So the agenda we have planned for today is talk about deep learning first. Sean will sort of level set what deep learning is just to bring the room up to speed. And then I'm going to be talking about Azure Databricks and how you can use Azure Databricks to solve some of the deep learning challenges that Sean is going to talk about. And finally, we have put together a cool demo for you, which kind of brings together all the concepts and sort of brings together Azure Databricks and deep learning. So with that, I'll hand it over to Sean.
Thank you. Right, let's talk about what deep learning is. I think it was about 3/4 of the room that maybe wasn't sure. They could explain deep learning in a paragraph or two. What is deep learning? It's this. This is the picture we keep getting shown when told what deep learning is. And there's some interesting points here. Deep learning it's a machine learning technique. So it's a way of typically predicting some set of outputs from inputs, given a whole bunch of examples. But typically that happens in effectively one shot. We take one step from the inputs to the outputs. And in deep learning, we use inputs to learn better inputs to learn those outputs. That is, we're trying to figure out what transformation of the data is more meaningful to predict the outputs. And maybe we do that over and over, and we stack layers and layers of it on top of each other. And pretty soon we have not just one little model, but a deep model. And it turns out that's powerful and effective as a machine learning technique. So as I say, deep learning, you could say they're multi-layered models. It's kind of like stacking models and training them together. You learn how to transform inputs into more meaningful features. If you've heard that deep learning helps build features for you, that's kind of true. Really, deep learning is trying to figure out what intermediate representations of your data are meaningful for the prediction problem you're trying to solve. And they're often called neural nets, and I think that probably goes back all the way to the 1980s when this technique was first invented or researched. The people felt that we could probably make some progress in AI by trying to literally mimic how the brain works and its neurons that are tightly interconnected. And it didn't actually get very far in the 80s just because no one had enough computing power to throw at it. And it wasn't really until maybe the last 10 years at best, maybe even 5, that people figured out how to scale up this idea, and it's really taken hold again. People also call this neural nets because we think in a way it maybe learns the way our brains learn. It learns by identifying transformations and layers of representation and features, not just one big transformation from very granular input to big concepts. And as a result, deep learning has made great strides in tasks like computer vision. You've seen it applied to driving, machine translation, things that we think of as human brain techniques, things that the mind is good at. Suddenly, deep learning is making some really big strides in. So that's why people are really excited about it today. The downside is it is very, very computationally intensive. I think of it as the triumph of brute force. All this modeling, all this stacking of layers, all this automatic feature engineering from huge data means a lot of number crunching. And the good news is it's all simple math. It's a lot of linear algebra, but there's a whole lot of it. And we'll come back to why that's important from a deployment standpoint later. I couldn't find a really good one picture that visualizes what deep learning does, but this comes pretty close. This is an example of a deep neural network that's trained to recognize images, to recognize that it's a cat or a bird or a motorcycle in an image. And what this is trying to visualize are these multiple layers that the algorithm is learning. On the left, we have a bunch of images. On the right, we have really labels. And in between, we have all the transformations of that raw image input that this model has learned, these convolutional layers have learned. And at the left side, the model seems to learn very fine-grained features, like a line or a bit of red next to a bit of yellow. And a step up, it learns maybe slightly more complicated combinations of those small features, like a diagonal line or a colored boundary. And as the layers go up and up and up, we start to recognize higher and higher level features, like an ear or a head or a landscape. And in the end, those are the types of features that ultimately help us predict what is actually in the picture. So the performance on this classification task is really interesting, but so is the representation that falls out in the middle. And I think this is why people are really interested in deep learning. It somehow mimics maybe how we think about problems, how we would actually break down and represent a complicated modeling problem. And you can, in this case of modeling images, you can actually visualize it and see it. And I think that's pretty cool. So where does deep learning get applied? Often to computer vision. The problems, just as in the last example, that's a classic application of deep learning for maybe classifying images. Likewise, it can be applied to streams of images, that is video, to tag video and recognize images in video. And that's why deep learning is powerful for self-driving cars that need to understand what it's seeing in front of the car from cameras. Generally speaking, time series analysis is also a good application of deep learning, where you may have patterns that occur over time, and you need to learn complicated patterns over different scales. And one particular example of not quite time series processing, but sequence processing is language. So when we speak a stream of words, but the relationship between the words is complicated, and the meaning is some complicated function of those words. And deep learning, recurrent neural networks are good at finding those levels of meaning and building up great models. So this is why people are excited about it, and I've got a little bit of bad news. Not only is it computationally intensive, but the deep learning part in the middle is really not even the hard part. This is from a Google NIPS paper from a couple years ago. The paper was all about technical debt in machine learning systems, and they tried to draw visualize the code that Google had to implement one of its key machine learning systems, and draw out these boxes according to the number of lines of code for each system. And it turns out the actual machine learning part in the middle was just a fraction of the code, I don't know, 5% or so. And most of the code they had written had helped with deployment of infrastructure, storage of data, transformation, monitoring of model performance, feature extraction, and so on. So the bad news is that deep learning is great, but deep learning itself is complicated and it requires a lot of computation. But to even get there, you've got to tick a lot of other boxes first. You need to figure out how to get all this data, how to store it at scale, how to apply computation to it, how to monitor these processes when they run, and how to deploy those models at the end. So we live in a world where we actually need a lot of things to go right in order to take advantage of this powerful magic called deep learning. In the middle, as I say, we have it's not trivial to run deep learning models just because they need so much computation, and that sometimes means deploying complicated pieces of software and specialized hardware like GPUs to have enough computation to throw at those modeling jobs. And modeling jobs don't write themselves. When we create them, when we tune these processes, it's typically a team of data scientists and data engineers working together that need to collaborate in an iterative way to model and assess and tune and evaluate and repeat and repeat. So we need to find a way for those people, those different roles, to work together in one environment. And finally, they all have to build these models on potentially lots of data and dirty data. We're trying to consume data that could be tabular or not, text, images that may have errors, gaps, and differences in formats, all in trying to bring it together in one environment and make some sense of it. So doing deep learning is not just about running some software and some specialized hardware. It's really a team sport that requires mastery of data engineering as well. And I like to think that that's where Azure Databricks from Databricks comes in. It's a platform for doing a lot of those things that you need to do in order to successfully apply deep learning. And Premal's going to give us a little bit of a walkthrough about what Azure Databricks is.
Thanks, Sean. So as Sean mentioned, two classical problems with deep learning. One is that it is compute intensive, and secondly, it's a small portion of your entire pipeline. So that green box that you saw is the deep learning portion, but you saw the bunch of other boxes that you need to do to get deep learning right. And that's where Azure Databricks, as Sean pointed out, comes in. So I'm just going to give you a brief intro about Azure Databricks. So it's the fastest, easiest, and collaborative Spark-based platform in the cloud. And it's a unique service because what we've done is we have Microsoft and Databricks, where Sean is from, have collaborated to create this platform. We have literally taken the best of Microsoft and the best of Databricks. They are the creators of Spark, so it's literally Spark on steroids. So we've combined these two together to offer this unique service. And if you think about this service, it is based on fundamentally three key design principles. The first is increasing of user productivity. So one of the goals we had in mind while we thought about this service and built it is that we want to help users enhance their productivity using the Databricks interactive notebooks, using a variety of languages, like R, Python, Scala, and SQL, because what we realized is enterprises have different needs, have different kinds of skills, have different kinds of data scientists. So this is really important, that how do they collaborate? So we have Git integration, we have version control. So as a bunch of data scientists are working on this, they really can collaborate to build compelling deep learning applications. So the philosophy for the productivity is that we want to make sure that you are focusing on your business logic and you're not thinking about sort of the whole setup that comes along with a Spark platform. The second is, enterprises today want the kind of guarantees that they get by being on Azure. So they want security, they want compliance, and we have tried very hard to offer that. So the platform is cloud first. It's built. It's a first-party service in Azure, and it basically helps the enterprise achieve all the security goals. So it has role-based access control, it has enterprise security and identity, it has all kinds of compliance built into it so that enterprises can take advantage of this platform. And finally, if you're building deep learning applications, you want to be able to scale without limits. So we have built this platform so they can scale globally without any limits. And the best part is that as you are building out a deep learning applications, the platform automatically scales up and down as per your needs. So again, the idea of management and idea of you managing the clusters or the platform is minimal or non-existent, and you're focusing on building that deep learning application that we sort of talked about. And with the service comes a whole bunch of other features, as I mentioned, role-based access control, AAD authentication, integration with Power BI. So if I go to the next slide, what we've realized by talking to customers is that one service does not solve all the problems. The Azure Databricks is a cloud-first Spark platform. It's a distributed computing engine. So with that, you need storage, you need networking, you need integration with different systems in Azure. You as a customer might want to build models and deploy them. So we have integration with Azure Machine Learning to deploy models as REST services. We have integration with Blob Store and ADLS to get the data from.
You're on that slide.
Oh, so sorry about that. Yeah, my mistake. I guess I haven't had lunch, so. So you can talk to SQL Data Warehouse, you can talk to Cosmos DW, and really we have made it a first-class experience so that you as a customer doesn't have to really think about hooking all these different things together. It's all a seamless platform that we provide. So how does Azure Databricks helps deep learning? And Sean talked about the three sort of main points in deep learning. One is that you want a highly performant pipeline. Again, coming back to that really compelling diagram of one green box and a bunch of different boxes. For all those different boxes to work, you need a really, really reliable pipeline. You need cutting-edge AI models at massive scale. So deep learning is compute intensive. It requires data. So how do you build deep learning models easily? And finally, how do you then have collaboration between different teams to then build these large deep learning models? So with the Databricks Runtime engine, you have an optimized and managed Spark that helps you build that non-deep learning pipeline that Sean was referring to. You can, the next slide we talk about the pre-configuration. So what we've done is we've taken some key deep learning frameworks and pre-installed them as part of the platform so that you as a customer doesn't have to worry about hooking again the different drivers together and dependencies together. And then the team collaboration, where you're actually building a model together, you're deploying a model. So we have integration on model deployment. So you can deploy your models at scale as REST services or batch. So from here on out, we're going to talk about the new features of Azure Databricks and how it really helps deep learning. So one of the things we released at Spark Summit is this Azure Databricks Runtime for ML. And basically what it is a pre-configured cluster with all the deep learning frameworks that we have heard that customers most commonly use. So there is Keras, there is TensorFlow, there is XGBoost, and there is also Horoward, which is a distributed deep learning library. Now, why is this actually useful? You could easily just take any open source packages, and Sean will probably show in the demo that you can install them as libraries. The thing is, some of these packages are simpler to install. Some of them are really, really difficult. So if you take the example of Horoward, which is a distributed deep learning library that's built on top of TensorFlow, it is quite a pain to configure. It is built on top of MPI, which is kind of an older message passing technology. So if you've tried to configure Horoward yourself, you'll kind of understand what I'm talking about. It requires MPI drivers, it requires dependencies, it requires you to wire up a whole bunch of things together to get Horoward sort of working right. So we have removed all that friction from you, and all of that is pre-installed now with this Databricks Runtime for ML. So it's a special cluster that you can just spin up, just like any other Azure Databricks clusters, and you get all of this at your fingertips. The second thing is that if you just program using Horoward, we wanted to give a simpler interface for you to be able to program Horoward in a simpler way. So we have this Horoward estimator, and Sean will go into much detail in the demo, that allows you to do distributed deep learning in a much more simpler way. So it, again, removes some of the complexity that comes with sort of native Horoward implementation. And finally, as you heard, deep learning is compute intensive. So you need multi-GPU, multi-machine support, which is actually, again, not an easy problem to solve. So we have solved that using this platform also. This is kind of my favorite part, where it's really fun to see how customers use deep learning and how they're making use of that in the business. So these are just examples of 3 customers that we work with. The first one is very interesting. They have retail outlets, so they have gas stations, and gas stations have these 7-Elevens. And the thing is, how do you make your workplace safe for staff and for other customers? So what they do is, if the car is pulling in from the wrong side of the gas station, or if the car is pulling in on the wrong side of the pump where the gas tank is not there, they kind of flag this as, this is an alert. Or if there's a bunch of guys come in and they're drinking and smoking, that's like an alert. So they're using all kinds of these events to proactively notify legal authorities to be able to be there and alert them so that they can take preventive measures. So this is a very cool use case, and it has made the overall workplace much safer for the customer, which is really awesome. The other area that we are seeing an immense amount of growth is in the oil and gas industry. Maybe some of you might be familiar with that, but these oil rigs are out in the middle of nowhere. They have drilling equipment, and they want to do predictive maintenance, so they want to use complicated time series and image analysis to figure out that when is a particular drill going to sort of fault, so that they can send people in. And these, they are right in the middle of the ocean, so they don't have like a cloud to connect to. So some of these models are deployed to the IoT edge, where they can score right there on the rig itself. So this is a very cool sort of application. And finally, a lot of progress in medical imaging. So they're looking at brain scans now. There's a customer who's looking at brain scans to sort of detect diseases, so different kinds of scans. So that's a really cool application. It's making a lot of difference in the health industry. Yesterday, I came across another use case, which I don't have it on the slide, where there's a customer that's building a chatbot, and they're using deep learning for entity recognition. So the chatbot recognizes entities and is able to respond in a much more fruitful manner to the person that's interacting with the chatbot. So with that, I'll hand it over to Sean for the demo and other specifics.
Right, let's work towards a demo. So for the half of you in the room that know what Azure Databricks is, I hope that was a recap. For the other half, I know you're probably wondering, what is it? It sounds amazing, I want to see it. Don't worry, I'll give you a walkthrough of Azure Databricks in a minute. I'm going to set up the demo with a little bit of a story, though, and use that to motivate why we're going to talk about some frameworks like TensorFlow and Horoward, which may be new to many people here, and why you care. And the story is about recommender engines. Recommender engines are pretty much old news these days. We've all seen them. If you've used Amazon or Netflix, you know that as you use the site, as you buy things, as you watch movies, it learns and it tries to figure out from your activity and others' activity what else you might like. It's an old and it's a popular machine learning use case. And I think amongst the most famous applications of recommenders is Netflix, who famously offered $1 million several years ago. I think this was probably 2006 or so, for anyone that could improve their recommender engine for their movie service. And it was part marketing for sure, but it was effective. It got people very excited about recommender engines all of a sudden. And in the end, I don't know if you follow the story, but there was a bit of drama at the end where a team submitted their final submission right before the deadline, and they got a great score. And then 20 minutes later, another team submitted their final submission, and it had exactly the same high score. And that team that had submitted 20 minutes earlier walked away with $1 million. Well, the team that walked away with $1 million was called Belcore, and you remember their name and their paper and so on. The team that almost won $1 million was the team that from, I believe, AmpLab in Berkeley, who actually built Spark in order to distribute the computations they were using to try and solve the Netflix prize. So a colleague of Mate Zaharia, who's kind of the founding father of Spark from AmpLab, was working on this prize and asked Mate to help him build a distributed compute framework to power their ensemble modeling. And they almost made it into $1 million, but instead they made it into Apache Spark, and I guess that's a good thing. So in a sense, Spark had its roots in Netflix, the recommenders in the Netflix prize as well. So how do you solve recommender problems? It's common these days to think of it as a matrix completion problem. You've got users, you've got items. You could think of it as a big table where users are rated movies and their ratings occurs at that particular cell on the table. And it's like a big matrix with a bunch of blanks. And if you can learn how to fill in the blanks correctly, then you can predict how users will rate movies, and you can recommend movies they'd rate highly. And it's typical in these contexts to maybe hold out a little bit of that matrix and that data and learn from the rest of it, and then make predictions and see how well your predictions match that bit of rating you held out. And maybe compute a root mean squared error loss to figure out just how good your recommender engine is. So this is roughly the problem. Given some predictions, some user item interactions, predict all of them and use that to rank items for users and evaluate this way. And one common way to do it, which actually did popularize itself during the Netflix prize, is called ALS, matrix factorization, alternating least squares. So the idea here is that the big user movie matrix, it's big, but it's sparse, and it's actually low rank. There's not actually a lot of information in there. Even though you and I and hundreds of thousands of us can watch thousands of movies, really there's probably a small number of preferences and for genres that explain all that. So what we try to do is factor that matrix as the product of two smaller matrices, low-rank matrices, whose product together almost roughly gives us back the actual ratings matrix. And if we can do that really well, that solves our matrix completion problem. The nice thing is that this is just a little bit of linear algebra, and there's known ways to do this decomposition, and they're efficient to scale up as well. So ALS, this alternating matrix factorization algorithm, it's implemented in Spark. It's widely known, and it's a popular way to build this model. What you get out of this for every user and for every movie is really a list of numbers. It's a vector that in a way summarizes what the movie's about and the preferences that the user has, in terms of maybe 10, 50, 100 numbers, not thousands and tens of thousands of movies. And in a way, I think this resembles what deep learning does. You have some inputs, which are the user and item ratings, and actually they're also the outputs you're trying to reproduce as well, so it's kind of like an autoencoder. But to learn it, you're actually trying to represent that raw input differently as these user and item factors whose product explains them. So you could say that ALS kind of resembles a shallow neural net. Not quite in the way it does its math, not quite in its structure, but certainly in the sense that they both try to produce these intermediate representations that are vectors of numbers and that are meaningful for representing the input and the output. So if ALS is a cheap and cheerful way to get a pretty good factorization, to get pretty good representations, I wonder if we can take that output and then apply deep learning on top of it. Use ALS's output as a starting point, and then stack deep learning on top of it to run further with that. build an even deeper representation that might even be better for predicting user product interactions. And this is also a pretty good general idea. Typically, at scale, when we're building deep learning models, we don't really like to train models from scratch. We often like to take models that are similar and maybe take most of their layers that have learned some generic features and learn some more domain problem-specific layers on top. So this is a nice idea to begin with, and we're going to use it as the basis of a demo here. Right. So let's get to some code. Before I show you code, and I will get to code in the end here, I want to explain a little more about the frameworks we're going to show off, what we're going to show. I'm going to show you Databricks, so I'll walk briefly through how you create a cluster and what the notebook environment looks like and how you run code. I'll point to some of the elements that are baked into the runtime in Databricks, the ML runtime. These are machine learning packages that are already compiled and optimized and built into that environment, so you don't have to install them as packages. And we'll point to some integrations with Apache Spark along the way. One of the punchlines of the demo is going to be using two packages, TensorFlow and Horovod, together with Spark to actually distribute the deep learning computations not just to one GPU, but to multiple GPUs across multiple machines. And that's actually harder than it looks, and we'll get to that here. What's TensorFlow? If you haven't heard of TensorFlow, it's probably the key deep learning framework in use today. In a way, it's a lower-level deep learning framework. It's kind of the assembly language that a lot of other higher-level frameworks sit on top of, like Keras, for example, and in this case, Horovod. And it abstracts out these matrix operations, tensors, in a way that higher-level libraries can build on to implement deep learning training pipelines. So TensorFlow does a lot of the magic to push down these big workloads onto GPUs and onto TPUs from Google. And it works really well, except the only asterisk there is it's always gotten kind of hard to scale up TensorFlow. And clearly Google's done it. They have some clever ways that they shard their computations across multiple machines and GPUs. And some of it's in TensorFlow, but I can tell you from experience that it's a little bit hard to use, especially if you're used to Spark. And one of the problems is that the model that deep learning needs to distribute is not quite the same data parallel model that we're used to in Spark. That is, the way we're used to splitting up problems to scale by sharding data and computing on data independently isn't quite what's needed for deep learning. And I think you'll see the same thing play out if you look at a lot of attempts to distribute many different deep learning frameworks. They're successful to different degrees, but they all seem to struggle to scale up across multiple machines. You'll see a lot of efforts, many built on Spark. And one of the problems here, there's just an impedance mismatch here. Spark is a data parallel framework, and workers don't really talk to each other in Spark. But in deep learning, they really need to talk to each other. And let me dig into a little bit about why and then how we can get around that. So if you're familiar with distributed deep learning, you've probably come across people talking about parameter servers. The reason people need servers for parameters is that the whole operation of deep learning is really to estimate the parameters of this model, all the values on these weights on these edges in this big networks. There's a lot of them. There can be millions and millions of parameters. And when you split up the data and try and train the model, all these different workers are coming up with their own estimates of the parameters and how they should change. And they need to constantly be exchanging those parameters so they all agree. So they need to be constantly averaging their estimates of the parameter updates or gradients. And that is a bottleneck when you've got tens or hundreds of machines trying to send gigabytes of floating point values to each other across the network. You quickly bottleneck on that service that's trying to coordinate all those updates. So you'll find that if you parallelize this naive way, you will not utilize your GPUs. You'll be waiting mostly on these parameter updates to come back to one machine and get sent back. It works, but it's not great. It doesn't even really fix things if you have multiple parameter servers, and this is how frameworks like TensorFlow try to get around it. It works better, but you still have to kind of carefully balance parameter servers versus workers and tune it and measure. It's not great. And the most interesting attack on this problem that I think we've seen to date is from Uber. They've open sourced a framework called Horovod. Horovod is, I think it's fair to say, it's maybe a better way to distribute TensorFlow workloads. A horovod is apparently some kind of Russian dance where people move in a circle, and it's appropriate because one of the key innovations in horovod is a better way to share parameters. So rather than have everyone share with everyone else n squared all their parameter updates, they basically share parameters in a ring so that everyone collects updates and shares and shares and shares. So at least it just has to go around in a ring. And then actually they split that up a bunch of ways, and all these parameters move in a ring at different rates. And it's just a different algorithm for sharing parameter updates that ultimately results in meaningfully fewer bytes to send over the network. That's number one. Number two, horovod actually depends much more on relatively old school technology, MPI interfaces, to have tightly coupled machines exchange data really, really fast. So it's using these frameworks for, you find in HPC computing, where the paradigm really is to have many tightly coupled tasks communicating intensely, and applies that to this problem, because this is really a classic HPC style workload. And between those two things, horovod's parameter sharing and use of these MPI frameworks, it can actually scale up almost linearly. So see the paper if you're interested, but it's made a meaningfully better distributed version of TensorFlow. So that's interesting, and that's something we would like to have on Spark. And I'll tell you that, as I've said, the model of horovod unfortunately doesn't quite match the execution model of Spark. Well, so Spark is going to actually move its execution model a little bit towards the horovod model in Spark 2.4. It introduces an execution mode called barrier execution mode that lets you gang schedule tasks. And if one fails, they all fail. And they schedule together, and they schedule closely together exactly to support workloads like this, more MPI-style workloads. So interestingly, Spark is getting, I would say, its first meaningfully new execution paradigm since its inception, just to support workloads like this. But right now we have a sort of beta version of integration called Horovod Estimator that stitches together horovod and the Spark Estimator framework from its ML Pipelines framework to let you get work done with horovod today. It's not a perfect match, but it does actually work, and there's better integrations coming post Spark 2.4. So let's take a look at what this all means. Alrighty, so as I promised, I'm going to also take the opportunity to show you Databricks a little bit for those that haven't seen it. This is Databricks. It's a first-party service in Azure. It's web-based. It's an environment that you log into to write, execute, and share code, maybe schedule it to run as well. And you do your work on VMs scheduled on Azure, but really on Spark clusters that are running on those VMs. And that's one of the key complexities that Azure helps manage for you. So if I were to create a cluster, I would go into a screen like this, and I can choose things like which runtime to include. Do I need GPU support? What Python version am I using? What types of instances would I like? How big do I want this cluster to scale or scale up, scale down? Not important, these details, but needless to say, I can define my cluster and then just go start it. And I've got one here started that is, I think, got a couple NC12 machines, and I've got 3 NC12 machines, each with 2 GPUs running. And that's the cluster that I can now connect notebooks to execute code. So I'm going to open not that one. I'm going to go into my workspace and open my notebook. For those of you that have used Jupyter or Zeppelin, very similar paradigm here. You have cells of code which you can execute, and different languages like Scala, Python, and so on. And you see the output below the cells. And you can run the cells individually. You can share these notebooks and edit them collaboratively. You can include inline documentation like some markdown here. So for example, I can make a new cell, and I think we're here working in Python, so you can do, if I 3 plus 4. Pretty standard stuff for notebooks. Oops, my cluster timed out. I'm going to restart that cluster. And the only bad news there is it's going to take a few minutes. So I'm going to restart that while I talk over the code. Then we'll come back, and I'll actually show you running some code. Let's get that instance back. I'm too responsible. I had it time out after 30 minutes to save money. Right, let's get back to that notebook. Fortunately, just like on the cooking shows, they show you how to cook something, and then they show you an hour later what they would have, what you'd see after you'd baked it for an hour. So I've actually run this notebook before. And one of the nice things about notebooks is you can see the output of the last run and talk about it and share it. So I can go ahead and show you the last successful run that I swear I did actually run live this morning. You can see, you'll be able to see by the timestamps. So here I am in Azure Databricks. My cluster's starting, sure. But I can go ahead and edit my documentation and my code. And as soon as that cluster starts, I can execute it. But you'll get the idea. This here, I'm using Python. You can actually mix and match languages within a notebook, but this one is all Python by default. And I'm starting by just reading the raw movie and rating data from some files off on our shared storage. They're Parquet files. So this is Spark code. I'm using Spark data frames to read these as data frames and just printing some basic stats. So I print that it's got about 1 million ratings. I know it's not a super big data set, but hey, it's a demo. And 27,000 movies. So within this environment, I can pretty print things like data frames and to display them. So I want to show a bit of this movie's data frame I loaded. It's got movie IDs and names. This is the millions movie data set. So it's a data set from, I think, the mid-90s. So all the movies are basically from the 90s. And I can show the ratings data set. And this is the data set we're actually going to be learning from. It's got user IDs, movie IDs, and ratings. And I think it had timestamps, but I pulled them out. We don't care. We just want these tuples. That's our input. So we can actually just use built-in primitives in Spark ML to build a recommender model from this using ALS. So let's do that first and see where we get. First, we just randomly separate out 20% of that data as a held-out test set from 80% that we're going to use to train, and cache those data sets because we're going to reuse them frequently, so let's keep them in memory. And great, so we've got about 860,000 ratings to train on. We'll test against about 214,000 later. I've copied and pasted that nice bit of documentation from the presentation. And here we go. We're going to apply ALS, alternating least squares. This is part of Spark ML, and here we're using it through the PySpark bindings. Just set up some parameters here, how many iterations to run, regularization, the rank of the user item matrices that we want, and tell it to go fit. And when we run that, we're actually not just running code locally, but invoking Spark jobs on the cluster. And you can conveniently click through and, oh darn it, since my cluster's not running, I can't see it. But you can click through and see the Spark interface for those jobs, where it shows you which tasks are running and if they failed, why they failed, and a bunch of stats about it. So you can quickly dig into the actual distributed execution of these if you like. But in this last execution, sure, pretty quickly fit this model. And then I need to evaluate it. There's some tools built into Spark ML to do that. We're going to evaluate the result as if it's a regression because we're kind of comparing numbers to numbers and comparing the root mean squared error. And if you let it evaluate the result on the held-out test set, we get about a 1.2 root mean squared error. Not very good. Not very good. I mean, okay, granted, I kind of handicapped it by just running 2 iterations and low rank for demo purposes, sure, but okay. You know, it's even if you ran it a little more, you might get a 1 or 0.9 RMSE. That's okay, but it's not great. I mean, we're off roughly by almost a full point in our ratings when we go back to predict. But the nice thing is, even though ALS is not a very different thing than deep learning, we can, with a little bit of code, pull out those vectors it created for us and go feed them into a different framework, into Horvath and TensorFlow, into maybe a shallow neural network, and see if we can train it one step further and improve on that. So this is some code that really implements that, some of that data munging to get the data out. We're going to pull out the user factors as a new data frame. And for example, here, for example, we see that for this user in this movie, these are the user features. So this is the vector of features, that represent the item, this particular item. This is a vector of numbers we think represents that user. This is what ALS has come out with as a representation for those items and for those users. It's going to be the starting point from which we're going to build a better model on top with a bit of deep learning. Just numbers, nothing to see here. A little more munging here just to get this data in the right format. I'm just going to skip past this and get to the deep learning part. So here we're going to apply TensorFlow and Horvath. And Bad news is TensorFlow is a little bit hard to use directly. It's a low-level language. The good news is it's not much harder to use Horovod and TensorFlow. So I think this section of code may only make sense if you're actually familiar with writing models for TensorFlow. To define a model, you really want, say, a function that can do a couple things, like tell TensorFlow about the shape of the model you want to build and help it evaluate it. But if you feed that model function to TensorFlow, it can go do its work. So this is really what it returns what TensorFlow calls an estimator spec. It's a specification for building this estimator, which is its word for a model. And this is how you would interact with TensorFlow. And the only bit that has to change when you use Horovod here is to substitute in Horovod's distributed optimizer. So the only thing Horovod is really overriding here is that key optimization step, which is really all of the deep learning process, sure, that's optimizing the parameters and learning the weights in the neural network. So if you just slip this in, it all suddenly works on Horovod. So that's actually all the integration you have to do. And in here, this is the actual model we're building. It's the definition is pretty simple. We're just going to train a simple 2-layer model where the layers, I think, have 20 or 30 features wide. A little more data munging. And then here we go. This is where I think we've added a little bit of value at Databricks. Horovod Estimator is the thing that connects Spark to Horovod and TensorFlow. So this implements the estimator API in Spark, which is a model building API. And given that model function, given a couple other settings like how many layers you want in your hidden layers and so on, it will go invoke Horovod on Spark, on that Spark cluster. And I've got my cluster back, so I'm going to go ahead and start this whole thing running from the top and then come back down to the output. So just to prove this works, print 3 plus 4, you get 7. I'm connected to a live cluster. I can run these things individually. For example, I can run a single cell and then see. Might take a second to warm up and get on the cluster here. What I should be able to see when I'm executing these distributed jobs to read that data is the status of the job. So again, as promised, I can click through to the Spark UI. Yes. And this is just the standard Spark UI that you may be familiar with, where if I want, I can dig down into all the details of the execution and see what's going on. But I don't have to. I can also just ignore that and look at the output. Anyway, so I'm going to go ahead and run the whole thing. But in the meantime, I'm just going to stay fast forwarded here and talk about what you would see when the output hit here. Right. So once you run this, what you would see here is a lot of the output from Horovod and TensorFlow, which is pretty scary, but you can kind of see inside here, it's running some MPI primitives like with MPI run and doing a lot of this complicated MPI stuff on Spark for us behind the scenes. You'll see if you cared to, you could scroll through and see some of the raw output here. So the training is starting about here, and it's done about 100 steps, 200 steps, 300. We're almost done here, 26,000 steps and so on. And you can see the loss going down. This is its internal estimate of how bad the model is, and it's roughly speaking coming down over time. Now, there's not a lot to see here. That's sort of the good and bad thing. There's not a lot of GPU-specific stuff in the code or the output. In fact, this same code would actually execute on a cluster with no GPUs. Horovod would still run, it just wouldn't use GPUs, because TensorFlow wouldn't use GPUs, and it's just the same. That's good in a way. It makes it very, very simple to move your code to more powerful clusters and machines, but there's not just a lot to see here, I'm afraid, other than the raw output of the modeling job. But if we then take the output of this neural network, which is also user and item vectors, and multiply them together so we got our predictions in the same way that we would with an ALS model, we can also evaluate how good those predictions are at the end. And the last part of the notebook just really tries to do that. It puts together the users and movies with their actual rating in the held out test set with the actual predicted rating from this model. Sometimes it's good, sometimes it's not so good. But on the whole, we will see you get an RMSE of about 0.84, which is a lot better. And if you ran this with a better model and tuned it a little more, you could bring it down and down and down. Now, in a way, this use case doesn't have as much to see because it's not an image-based deep learning application. But I think you can appreciate it would be just as easy to apply these tools to a problem where you were actually processing images and so on. This actually is not specific to any particular deep learning problem. I can use these tools to, yes, process video, yes, process image, to natural language processing, but also maybe take it off-road and apply it in ways that are a little bit unconventional, like putting deep learning on top of the results of another model to further improve it through transfer learning. That is most of what there is to see here. The rest of Databricks, for those that don't know, has just some other features that support this core notebook-based execution functionality. For example, if I like, I can schedule this notebook to run every night as a job and which cluster it runs on and so on. I can share these notebooks, so Premal and I can collaborate at the same time on a notebook, even see each other's updates as we work together. And there's also some support in here for easily adding libraries to your cluster. Maybe you're just using NumPy and scikit, in which case it's already built in, but maybe you want to bring Stanford NLP or something to your project, in which case you can just attach a library to the cluster, and it's all available for you. Anyway, so this will execute. I think we're probably now back to the point where it is executing that deep learning model. Here. And from the Spark side, we can see this is kind of what it looks like from the Spark side, which is these are the wrapper tasks on the Spark side that are really driving the Horovod jobs. And again, you can see in real time this output here from Horovod. Excuse me. Where it's crunching away. Moving oh so quickly because we're using several big GPUs. So I think that is what I've got to demo today. I hope that we gave you a little bit of a taste of what it means to do deep learning and why you care. Some of the challenges around it, setting up your data, transforming it, stitching together libraries into the platform, collaborating with people to get the job done, and ultimately using some complicated hardware and software to get some of these magical results people are getting from deep learning, and why something like Azure Databricks is a pretty decent place to do that. Whether you are trying to analyze images, whether you're trying to analyze text, or indeed just trying to use deep learning to get some better results out of an existing model. The good news is this is only going to get easier with Spark 2.4, with better Horovod integration. It should become something that just works, to throw a bunch of big GPUs that are now available on Azure at problems like this and make it go bigger, make it go faster. Any additional words to add, Premal, before we take questions?
I think that's all. Thanks, Ron. So just want to open it up for questions. Wanted to give enough time for people to sort of discuss if you wanted to talk about something or ask questions or.
Okay, thank you. While we do that, I'm going to switch back quickly to our call to action here. Please evaluate the session. Here's the QR code if you've got your app. I'll leave that up for a moment here. Well, thank you. But
thank you. Yeah, thank you.
And then I'll leave that up for you.
And any questions on deep learning or on Azure Databricks? It doesn't have to be deep learning. It could be a question on Azure Databricks too. If you guys have any questions about the platform or any other features, you can come to the
to the mic. Race to the mic.
You talked a lot about Python. What about R?
What about R? Sure. So you can also use R in Databricks here. It's just you can even mix and match to some degree R and Python and Scala in the same notebook. So when you're using R, you're just running an R interpreter. You can use Spark R to interact with Spark or Sparkly R. There's two libraries for interacting with it, or really any other package you want. The only bad news is, the integrations with deep learning frameworks tend to be all in Python, but there are some for R. Last thing I'll note is if you like RStudio, there's a pretty nice RStudio integration in Databricks as well. You can use the RStudio interface on Databricks and use it as basically the notebook interface if you subscribe to the RStudio server.
You had a question? Yeah.
Is there another one?
Yeah, I think.
More here.
Go ahead.
It's only a simple question. If I'm new to Databricks and you had a lot of code in the workbook, where do I start? Do I get all this code in a new Databrick, or is there a resource where I can copy code from?
So you've got a lot of existing code. How do you get it into Databricks?
I don't have anything.
We don't have any,
Oh,
sorry.
I have ideas and things I want to do, but I'm new at Databricks.
So if you're new to Databricks, where do you start? The good news is you can use it for free. There's a Databricks Community Edition.
Yeah, we have so on Azure Databricks, you have a 14-day free trial version. So you can try it out completely free of charge. And if you go to docs.databricks.net, there's a whole bunch of documentation. And in fact, we have a bunch of examples in data analysis in classical machine learning. So if you just want to use linear or logistic, and even there is a Horvath estimator example there if you want to just take it. And it's as easy, if you go to the documentation, it's as easy as you just open the link, you can open the notebook in your workspace and just execute it end to end. So these are working notebooks end to end.
Right.
So there is no assumption, no dependencies on any data you have to get. It's all self-contained. So that should be a good start, I think, that you might want to explore a bit.
Okay, thanks. And what was the URL again?
Sorry?
Docs.databricks? Was it docs.databricks?
Yeah, docs.azure-databricks.net.
It's right here.
Right.
That's right, it's right there, yeah.
And there's actually a link to it from within Databricks. There's a training and tutorials link at the top level that just takes you there. Yeah.
So when you run your code, how do you know it's running on GPU cluster, not a CPU? Or you compare with a CPU cluster, do you see the significant performance improvement?
Okay, so how do you run on a GPU cluster versus CPU, and how much difference does it make? Well, to use CPUs in your cluster, you do a couple things. When you create the cluster, number one, you're going to want to choose one of our runtimes that includes GPU support, and probably our one that also includes the machine learning runtime. So for that, in that case, this is right now we're still at 4.1 ML beta with GPU support. And then it'll force you to choose a GPU instance type here for the driver and workers, so like a NC12 beta. And then everything else should just work. You should be able to use GPUs. When does it help? Well, I'd say it's always pretty much a win to use to train on one machine with a bunch of GPUs. A lot of frameworks are good at that. But when their GPUs are on the same machine, that communication cost is no big deal. Across multiple machines, yeah, it's a problem. And things like Horvath help with that. But still, you don't get quite linear speed up. So I guess there are cases where you really do need multiple GPUs across multiple machines. I still would only do that if you really needed to. I would exhaust the possibilities on one big machine with a bunch of GPUs first. And you can do either one here.
Those who are starting new to this, is there like not even knowing about ML or anything like that, is there like a hello world kind of starting point, getting started?
So if you're new to Spark and machine learning as well, where do you start? Yeah. Sure. So I think, again, the training materials have some pretty good hello world examples from machine learning. Let me see if I can find one here. So I might start on the For Data Scientists link. So our documentation actually embeds some of our notebooks. I don't know why it's not. Here we go. Yeah, loading. Here we go. So it actually embeds some of our notebooks so you can clone and use directly. I think these provide, I think, fairly gentle walkthroughs of reading some data here. This is reading just some CSV data, and doing basic manipulation with SQL, displaying that. And here, for example, is an example of using SQL commands rather than Spark in Python, rendering it as plots and so on, and then gently getting on into running some basic models. Beyond that, anything on the internet you find that about, say, scikit, you can run that same scikit code here. If you find examples in PySpark, it all runs here too. There's no special language here for Databricks. It's just Python and its libraries, and PySpark especially, and likewise with Scala, R, and SQL. We've got an O'Reilly book with examples too.
I also wanted to add that the best way to sort of learn is just by doing it. So the more notebooks you execute and try to sort of understand what's happening in each cell, and there's extensive documentation on all these things. So would recommend that you actually run through the notebooks, create a cluster, run through it, go through each cell, see the outputs. Just by looking at the inputs and outputs itself, you will actually ramp up. It's pretty comprehensive. So.
We have training too.
Yeah, there's a lot of training materials out there. That if you go to the Databricks site, also there's a lot of paid and free training. So there's enough to kind of drown in, honestly. So.
Okay, another question. If I'm starting experimenting with Databricks, I'm on an MSDN Azure license. If I shut down the cluster, is that okay? Then there's no billing incurred?
Yeah.
Okay, great.
So if you there's an option called maybe Sean, the terminate after 120 minutes of inactivity. That's a perfect way to save cost, because even if you forget, although I should mention that you auto-scale, so Azure Databricks auto-scales, but even if you don't want that, if you want to just terminate the cluster, you can do that. The nice thing about termination is that when the cluster comes back up, all your libraries are already installed. So it's not that you have to go and reinstall everything that you have done on that cluster. So that's the sort of advantage of that.
Thank you.
Thank you.
Yeah, it's a good point. Databricks is charged as consumption-based pricing. So as you're paying by the hour for your instances or minute, you're paying roughly by the same, in the same way, paying according to how much resource you use to Databricks. It's consumption-based.
Any other questions? Yeah.
So for your demo, you did the ALS model, and then you used the results from that for the deep learning. Why would you want to use the results from that rather than just go back to the source data?
So why do we do this? In a way, it was just to make an example that I wanted to make. We could have done a couple things better here in reality. Number one, I could have made a better ALS model to begin with. I didn't really let it run that long. So that's one thing we could have done. But was your question, why not just skip ALS to begin with and just train it? You could also do that. If I had to concoct a reason why you might want to do this, ALS is is fast. So the iterative process it's running is much faster than you would training even a 2-layer neural net. So at scale, maybe it actually would make sense to run this a little bit to get some user vectors that are roughly right, and then bring out the big guns and train that further in a deep neural net. In this example, I think that's a little bit contrived, but in other real use cases, you definitely might take an existing model and chop off a couple layers and reuse the whole thing rather than train all that. Or indeed maybe use another simple model to get some good initial parameters and then feed it in. So these techniques come up even if this particular example is, well, I just wanted to use it because we think we came up with this because of the Netflix and Spark connection. That's why.
So how do you deploy the model after you build the model?
How do you deploy the model?
Yeah.
So go ahead.
So I wanted to mention, so there are a couple of ways. One is that if you want to deploy it as a web service, so we have, as I mentioned earlier, we now have integration with Azure Machine Learning services. I don't know if you went to some of those sessions, but they have an SDK with which you can just run it in a Databricks notebook, and you can deploy the model as a REST service. So that's kind of one option. I think for batch scoring, also you can utilize your Spark cluster itself for scoring batches, if that is a scenario that that works better with you. So you can use deployment. Comes in several flavors. So depending upon your scenario and whether it's sort of more request response, real time versus more batch, there are different. Sean, do you want to add anything to that?
Sure. The batch scoring is the easy case. If I just want to apply this scoring to a bunch of data, that's a good use case for Spark. And that's actually what's happening here at the end. From that model, we're just using its prediction function as a UDF, and I'm using that to apply to a bunch of new data, to score it and then actually evaluate it. Could easily do that with this output to go run this against a bunch of new data. And that could also be applied to a stream of data with Spark Streaming. So the streaming and the batch use cases, I think, are pretty straightforward. The only tricky part is serializing that model and maybe loading it later. And there's a lot of support for doing that automatically. A couple caveats, but that generally works. If you're interested in real-time scoring, have a look at a new open source project we've got called MLflow, whose purpose is, among other things, to help serialize models and make them portable and to systems that let you serve those models as REST APIs. So there's also a nascent real-time option there too in some cases.
I saw movie ID you used as one of the parameters for for the prediction. Inside the movie ID, do you have another set of data, like who's the actors or?
Right, so here, are we using anything about the movie? Because at the top I actually showed, we know at least the title of the movie. In this model, no, that data is not used at all. If we knew the director, no, we're not using that. Here it's strictly based on the ratings, that's all. But certainly that's one of the interesting things about deep learning. It's kind of a good place to throw a bunch of different types of data at once and let the model sort out how to put it together. So we could, if we were expanded this, join other features like genre, year, as features in a bigger deep learning model and let the model crunch that. And I couldn't do that with ALS. ALS really only works on rating data. But with deep learning, we can design some architectures that could actually load in different types of parameters as long as we can convert them somehow to numbers and go for it. But not here. We weren't doing that here.
About roadmap, are you guys planning? I see a lot of IBM and quantum computer. Are you guys on the roadmap for using Azure Databricks over quantum computing?
Is quantum computing on the roadmap for Databricks? I've not heard that.
I've heard that. I mean, I've heard that for the first time actually, but would love to maybe sync with you offline as to what are you, what kind of scenarios do you have, so we can at least put that on the roadmap. But right as of now, we have not thought about in that particular area. So it'll be interesting to speak to you, offline on that.
I'll tell you one of the key focuses for the ML platform team is this Horovod integration. We think this is one of the bets I think Databricks is taking, that this is going to be the right way to do distributed deep learning. So there's a better version of the integration coming out post Spark 2.4.
Just to follow up on the other chap's question, we've got CPU, GPU. Any other hardware that might be coming underneath that will help with libraries and stuff?
So what libraries can this use? What types of hardware can these libraries use?
Google have TPUs. Is there any other research hardware or emerging technologies that might be offered for Azure?
So are you talking about like FPGAs kind of scenarios? So we have, in Azure Databricks today, the deep learning model, so if you build a model with ResNet 50, for example, you can use it to deploy to an FPGA device. So which is, because now you have Azure, with FPGAs. Although for Azure Databricks at the moment, we don't support FPGA hardware yet. But that's definitely on the roadmap.
Right, so it's on the roadmap.
Yeah, yes.
Okay, thanks.
Hello. To studying this today's demo, is it possible to downloading this source code from something like GitHub or something?
If you email me, I'll give it to you. I'll have to double check if we can publicly send it out. There's no private data here, but the data source here is on our internal mount point in a bucket. So I'd have to kind of help hook you up with the data. But
yeah, and I have an offline copy too. So one of us, if you can email, we'll be happy to share. I think we have the email on the next slide. Yeah. So you can feel free to email any of us, and we'll happy to share the notebook.
Yeah.
Thank you.
Sure.
Yeah. Are there any other questions or comments? So Sean and I want to really thank you for your time. Really appreciate you guys being here and being patient and listening to us. I hope you have a nice rest of the day.
Thank you.
Thank you.
Take care.